Okay, so let's get started with some introduction to differential equations. So introduction to ordinary differential equations. Very briefly, for more details, you can go over the playlist on the course of differential equations. And if you want, probably it's worthwhile to just go over I would say the first lecture or two. But not more than that, because I don't think we're going to use more than that in this class. So suffices to say that, generally speaking, a differential equation essentially is any equation in which the unknown is a function. Any mathematical equation, sometimes there's a confusion on the terms, right? I mean, people call equations pretty much any math writing. But an equation means a mathematical expression in which the goal is to find an unknown. And in the case of differential equation, the unknown is a function. Let's say a function denoted by f of x or y of t, p of t, and so on. So the unknown is a function, and the ODE for the equation to be called differential equation, the equation itself must contain at least one derivative of this unknown function. So the equation itself should contain terms like f prime of x, dy dt, dp dt, p double prime of t, and so on. We're going to focus just on the equation that contains only the first derivative, because these are the ones that appear in the models that we're going to work with. More than that, actually, if you go through the theory itself, you will see that from a theoretical point of view, you could always change a higher order equation into a first order system. So you can always build a theory just based on first order systems. And deal with that later. Now, the reason why modeling work involves just differential equations of the first order, the ones that contain just the first derivative, is because most of the models essentially state something about the rate of change of a quantity. You know, if you have a population, for example, that changes with respect to the time, you build in that equation the positive and the negative terms. The birth rate, immigration in the community, whatever the positive contribution to the rate comes to be, that appears with a plus sign in the derivative. Whatever negative contribution is with a negative sign. Furthermore, you will see that the variable of the function is t, because, and we're going to use t from now on because it denotes the time. So all the models we're going to deal with are models that track the population in time. The math doesn't care if t denotes time or not, but because of the use of differential equations in the context of these models, that's why we use the t, the time notation. And another convention to make here is to not actually specify always this time variable in the equation, just for the sake of convenience. So if we give an example of a differential equation, let's say you write a differential equation that involves the first derivative of y, and then it's minus 3 times t times y of t to the power 2 plus 3 y double prime of t times, let's say, y of t to the power 4 equals, let's say, 0. I don't know. So this is basically just random stuff, because I'm not intending to solve this, obviously. Just to give you an example why the convention is made to not mention the argument of the function all the time. It's just for the matter of convenience, because if you notice, if I write the function explicitly, and if I write y of t, y prime of t, every time y appears in the equation, there's just too many parentheses to actually track, and it becomes really tedious and not really necessary if you think about it. So if we know that y is the dependent variable, this is how it's also called, this unknown function. So we know that, in fact, y doesn't stand by itself, it's just a shortcut for y of t. Then we can rewrite the above equation without mentioning y of t all the time. and it's more compact, and it's pretty straightforward. Now, in the context of modeling work, you have to be careful because we're going to have lots of symbols and letters, and it's very important to know at all times which are the dependent variables and which are the regular variables or constants for that matter. So for example, let's say we're going to talk about in more details about this obviously, but let's say we have an epidemic model in which I denotes the infected people at time t. One of the frustration of people going through the modeling courses is that there's just not many numbers in the equation. So people are used to seeing in the classical courses of differential equations examples like this, like for example, solve, the equation y prime equals, let's say, I don't know, 3 minus 2 times y. That's one of the ODE we can easily solve, okay, involving constant coefficients. Remember again that y really stands for y of t. But besides the unknown, the dependent variable, everything else pretty much is a number. And that happens in most of with the exception of word problems, but most of the time, most of the homework in differential equations deal with expressions like this. Now in math biology, if you compare, everything is a variable for a very good purpose, which will become obvious as the time goes on. And then it's important to make the distinction between the unknown and all the other parameters. So for example, an equation involving the infected people at time t may appear like this, dy dt. Okay, so far not much of a difference than this example, but then you'll see terms like, let's say, lambda s times I minus mu times I minus d times I. Again, not to get too quickly into the crux of the problem that we're going to deal with later, we just focus on notation here. One of the issues here is that in models like this, some of the letters will denote regular variables, some others will denote dependent variables. So for example, obviously I is not just a constant. I is a function of t. Like I said before, it infected people at time t. You will see later that s also is a function of t. Those will be people who are healthy that can be infected, or the so-called susceptible. And then anything else is a constant. So for example, lambda could be an infection rate. I mean, it is an infection rate in the way I wrote it here. And more on how this infection term is built will be discussed later. Mu, the Greek letter, could be, for instance, the natural death rate. And D could be the, let's say, the disease death rate, additional mortality because of the infection, if the infection is in such a way that it causes additional death. So you may wonder, why can't I see actual numbers here? For example, an actual number for the death rate, an actual number for the disease death rate. Well, because the short answer is because we try to build theorems. And the long answer is that the model, if it's worth anything, it should be applicable for a wide variety of data. So you do the math in as general setting as possible. Then you're going to basically try to fit these parameters to real data, maybe use it in a different context, in a different community, and so on and so forth. So if I derive a result on the model with an actual number for the death rate here, then the result will be very specific to that number. And it's extremely restrictive. Okay, a more important question, for example, is to say, okay, how big or how bad the disease should be. That is to say, what is that value of D or range of D that will cause, let's say, the disease to maybe wipe out 50% of the population, and so on and so forth. So questions like this are not suitable to putting a number to begin with, because an answer to the question I just asked is an inequality. The answer will be, for instance, well, if the death maybe is greater than some number, let's say 0.3, then maybe something will happen. So you must keep the variables unspecified or the parameters unspecified in the model when you analyze it. And so to go back to the notation, because we made a little bit of a detour, this is an intro class on the notation, it's very important to always remember the meaning of the variables, which are the terms that are actually unknown functions or the dependent variables, and then which are the constants that will have a biological meaning themselves, of course, and so on. As to the name of the variable, whether you use Greek letters or the regular letters in the alphabet, this has to do more with tradition or habit. I don't have more insight beyond that, to be honest. It's just that Greek letters are used typically in biological models to denote various things. And once you use them in a specific role, you get used to them in that role. And it will actually be easier to keep on using the same variable. It has to be somewhat suggestive, right? I mean, Greek letters typically, if it's not a Greek letter, try to make it suggestive. For example, D from the death, maybe B or beta for the death, and so on and so forth. So this is what I have to say on the matter of notations of differential equations. And on the next part of this lecture, we're going to go over solving. This is also provided in the lecture notes, obviously, but let's actually go over an example of solving a first-order linear ODE. So we're going to have a formula for that. So stay tuned.